Welcome to your first day of running practice. Who here knows how to run? Okay, that's exciting. Let's see it, okay? 3, 2, 1, go! Okay. Come back. What? What were you all doing?
Running extremely efficiently, of course.
You weren't using your hamstrings.
What's
You
a
look
hamstring?
like a penguin. And I don't even know what you were thinking. Today, we're gonna go over why we use our hamstrings in the sport of running and how to run.
The hamstrings are a group of skeletal muscles at the back of your thigh. There are 3 hamstring muscles: the semimembranosus, which is closest to the middle of your body and is responsible for flexing your knee joint, extending your thigh, and offering medial rotation; the semitendinosus, which is between the semimembranosus and the biceps femoris, which has a very similar function to that of the semimembranosus; and the third, which is the muscle that we are going to be focusing on in our video, the biceps femoris, closest to the outside of your body. The function of this hamstring muscle is to flex your knee, extend your thigh at your hip, and rotate your lower leg from side to side when your knee is bent. The biceps femoris is a 2-headed lateral hamstring muscle located in the posterior thigh, connecting your pelvis to your knee, essentially. And it plays a key role in knee flexion and hip extension, and also contributes to the stabilization of the pelvis. It is made of 2 heads: the long head, which originates from the ischial tuberosity of the pelvis, and the short head, which originates from the linea aspera on the posterior surface of the femur. The hamstrings in general, and specifically the biceps femoris, are muscles which extend the knee and flex the knee. The hamstrings play an important part in the complex gait cycle during walking and running, especially important in sprinting, which absorbs kinetic energy and protects the knee and hip joints. During the swing phase of walking, when you're bringing the knee back up or swinging it down, the hamstrings decelerate the forward motion of the tibia, and the biceps femoris is integral to this function.
Now that we have a general understanding of muscles, let's see how they interact with bones and joints to create movement. Muscles generate force, and bones act as rigid bars that pivot at joints, forming levers. These levers allow us to move efficiently with different mechanical advantages. In this section, I'll be going over the 3 different types of levers, which are the first class, second class, and third class lever. A first-class lever is when the fulcrum is between the effort and the load. A common example of this would be a seesaw, as I'm drawing here, with a person on either side, so when you push down, the other side will lift up. Another example of this could be our neck and our head. So the spine is the fulcrum, and our neck muscles provide the effort, whereas the weight is the load. These levers are useful for balancing forces and stabilizing motion. A second-class lever has the load positioned between the effort and the fulcrum. So as you can see here, I'm drawing a wheelbarrow, and the fulcrum is the wheel, and the handles provide the effort, so the person's lifting up the wheelbarrow, and of course the load is dirt or whatever you're carrying inside the wheelbarrow. This is also really similar to when we stand up on our toes. The fulcrum is the ball of our foot, and the effort comes from our calves or other muscles pulling up. And then the load is our body weight. This type of lever is great for increasing force output, which is why it's commonly found in lifting weights and stuff. And finally, we have our third class lever, which has the fulcrum on one end, the effort in the middle, and the load on the opposite side. So here I'm drawing a leg with the knee as the pivot point or fulcrum, the effort in the middle, and the load or the weight of your foot at that very end. This lever is most common in the body because it allows for greater range of motion and faster movements, but it requires more force. So as I said earlier, your legs can be a third class lever, and we have the fulcrum as the knee joint, the effort of the hamstring muscles pulling, and the load, which is your lower leg and foot. And so I'm just redrawing the lever right here, side by side with the leg, so you can see how that works. And due to the arrangement of the third class lever, the mechanical advantage is actually a disadvantage, which can be proven with the equation MA is equal to the output force divided by the input force. And in this specific example, we can also use the effort of the arm divided by the resistance arm. So the effort arm is the distance of the hamstring, so near the knee joint to the actual knee joint, and the resistance arm is the distance from the knee joint all the way down to the foot, so the length of the whole lever, I guess you could say. And since the effort is applied so close to the knee while the load is on the other side almost twice as far, the effort arm is much shorter than the resistance arm. So when you plug it in, we get a mechanical advantage that's less than 1.
When we're doing these skips, we're practicing this pulling motion of the hamstring. It's up, get your knee drive up, extend out, and then instead of landing there, the hamstring pulls back underneath. Just really exaggerating that motion so that when we're running, it looks better and is easier.
Here's a video of Maggie running in slow motion. Now let's take 2 freeze frames, just seconds apart, to see the motion of the hamstring. The left freeze frame is just right before the right freeze frame, and you can see that the foot is hovering just above the ground in the left freeze frame and has just landed on the right freeze frame underneath Maggie's hips. And we know that this pulling back action of the lower leg is done by the hamstring. So as you can see, the angle from left to right has decreased as the hamstring has pulled back the lower leg. Zooming in, we can see that the knee is the axis of rotation. The upward force applied by the hamstring on the lower leg is being applied right past the knee, as this is a third-class lever. In order to find the rotational force, or torque caused by this upward force, we must also consider the radius, or the distance from the force applied to the axis of rotation. There is also a downward force, the weight, mg, of the lower leg, which is a distance r2 from the axis of rotation. There are 2 torque equations for each of the 2 forces. The first torque equation is for the upward force from the hamstring, and the second torque equation is for the downward force, or the weight, of the leg. We know from the previous freeze frames that as Maggie is running and her hamstring is pulling up on the lower leg, the rotation is clockwise, and clockwise is conventionally the negative direction. This means that the first torque equation is negative, as it's the torque caused by the upward force, and the torque that would cause it to go counterclockwise is positive, and that's the torque of the downward weight. In these bottom drawings, you can see all of the different variables laid out, including theta, which is found as the angle between the force vector and the vector r, or radius, from the axis of rotation. Combining all this information, we can make a sum of the torques equation, which is the positive torque minus the negative torque. We know that the overall torque is negative because the leg is moving clockwise, the negative direction. So this means that the torque created by the hamstring is greater than the torque created by the weight of the leg. The torque caused by the hamstring is greater than the torque caused by the force of gravity. We know this is not due to the radius because the radius for the downward force, force of gravity, is the distance from the knee, or axis of rotation, to the center of mass of the lower leg, which is much farther than the radius of the axis of rotation to where the hamstring attaches, which is just past the knee. The angle theta between the force and the radius is greater for the torque caused by the hamstring, and this partially contributes to the torque created by the hamstring being greater than the torque created by the lower leg. It is more difficult to compare the value of the 2 forces because theta and radius can easily be seen from the diagram, while the force magnitudes cannot be. That being said, it is likely that force 1 is greater than force 2 because the total torque is clockwise, and force 1 likely contributes to the torque from the hamstring being greater than the torque from the downward force.
Have you ever wondered why sprinters and middle distance runners wear spikes? I mean, like, what even are these? Why do we do this? Well, it actually has to do a lot with the hamstring. So when you're running, you want to be landing right underneath your glute. So you're in a line like this, you have a slight bend forward, you're snapping up your leg and you're pulling it back to land right under your glute. That is the way to run with the most efficiency. You get the most force into the ground, you have the best energy return, and you're less likely to get injured. When you're running in spikes, it forces you to do that. So a lot of people when they run, they don't engage their hamstring and they do something called heel striking, where they land on their heel. However, if you look at the spikes, they have a curve, right? My heel is automatically above my toes, which means that when I'm running, I'm forced to be up on the toes. When you're up on the toes, it's really hard to land in front of your glute and have it feel natural. So we optimize our hamstrings automatically when we put on these silly little bright pink shoes. Okay team, let's see how your running form has improved after our lesson about the hamstring. 3, 2, 1, go! Woo, that was a lot better. Okay, come on back. Come on back. Okay? So, what have we learned today?
I learned that putting your foot down right underneath you is the best way to run efficiently, and the hamstring is what lets you do that.
And I learned the hamstring is a third-class muscle. I learned how to run faster backwards.
That's amazing! Success!